So the next topic in this section, this is still section 3.8, is the derivative of an inverse function. Um, we could have used this principle actually to find the derivative of natural log, since natural log is just the inverse of e to the x. But I thought it would work better in the context of a slightly different example. Recall that in order to find we did this in the pre-calc unit at the beginning of class. In order to find the inverse of a function, what you do is you solve for x in terms of y and then just switch y and x. So what I've put up here in purple is the function y equals x squared. If I solve for x in terms of y, what I get is x squared equals y minus 1, and then that means that x is equal to the square root of y minus 1. And by the way, note from the fact that I've only put half the parabola here that I restricted the domain of this function so that it's just x greater than 0. Recall that if I had put in the entire parabola like that, then I would have failed the horizontal line test. The function would not be one-to-one, therefore not invertible. I know that's a little blast from the past from several weeks ago, but you should remember that. So anyway, the point is that if I use just the right side of the parabola, I can invert it in this way, and I get the function x equals y minus 1, which actually you see over in green, so I'll put it in green here. Okay, so notice that the slope, notice that the 0.25 appears on the purple function. What may not be immediately apparent is what the geometric relationship is between these two functions, and the answer is that one of them is just the other reflected over the line y equals x, which I've put in red. And when you do this, when you reflect over the line y equals x, what you'll see is that we actually did this also in the pre-calc unit. That means that there's a point on the inverse function that is simply the coordinates of a point on the regular function switched. In other words, 5, 2 is a point on the inverse function. You can actually verify that 2 is equal to the square root of 5 minus 1, or the square root of 4. So that is in fact a point on the inverse function. Now, let's pretend that you didn't know how to find the derivative of y equals square root of x minus 1. There's a way that you could find it from the purple function at the given point. So first of all, let's find the slope of the tangent line to y equals x squared plus 1 at x equals 2. So if I say that f of x equals x squared plus 1, then that means that f prime of x is equal to 2x, so f prime of 2 is 2 times 2, or 4. That's the slope of the tangent at x equals 2. If I were to draw in this tangent line, it would have a slope of 4. Now, the question is, what is the slope of this tangent line? I'll draw it in green. A couple of things to note. It certainly seems to have the same sign, that's SIGN sign, as the slope of the purple tangent line. In other words, they're both positive slopes. Also, kind of looks like the purple line is very steep and the green line is very shallow, and this turns out not to be a coincidence. The fact is that if we found the slope of this line, just using the slope of that tangent line, just by using derivative rules to find the derivative of square root of x minus 1, we would find that the slope of this tangent line is 1/4. In other words, the reciprocal of the slope of the purple line. So the purple line has a slope of m equals 4. The green line has a slope of m equals 1/4. So there's a rule that allows us to do that, and basically what it tells us is that if 2, 5 is a point on the original curve, then 5, 2 is a point on the inverse on the curve of the inverse function. And if the slope of the tangent, in other words, if the derivative of the original function at x equals 2 is m, then the derivative of the inverse function at x equals 5 is 1 over m. The thing to also recognize before I show you the formula is that 5 is equal to f of 2, and 2 is equal to f minus 1 of 5. In other words, if the inverse function, just to be clear, that this is f of x and this is the inverse function f minus 1 of x, or f inverse of x, we can write 2 as just like I'm taking 5 and plugging it into the inverse function to get 2. this becomes an important symbolic notation in the in the formula that I'm about to give you. So here's the rule for the derivative of an inverse function. If f inverse is the inverse of f, then the derivative of f inverse evaluated at x is the reciprocal of the derivative of f at f inverse of x. That's exactly what we have here. Translated into this graph, what you'll see is that f minus 1 of 5 prime, in other words, the derivative of f minus 1, which, by the way, the book also writes this way by putting the prime there. You can do it either way. That derivative at x equals 5 is equal to 1 over the derivative of the original function evaluated at f inverse of 5, where we know that f inverse of 5, in other words, if I take 5, that's the x value there, and plug it into the inverse function, that's equal to 2. So this is equal to 1 over f prime of 2, which we know from looking at the purple graph is just 1 over 4. So this is sort of a geometric depiction of what the relationship is between the derivative of a function and the derivative of its inverse. So I've just put up here what the rule is for the derivative of an inverse function. Like I said, if f inverse is the inverse of f, then the derivative of f inverse is 1 over the derivative of the original function evaluated at f inverse of x. I've also put up here the steps, so if you're solving a problem, you can simply follow these steps to determine how to find the derivative of an inverse function. So here's an example of how we can use the rule for derivatives of inverse functions. Let's let f be an invertible function and suppose that the line tangent to the graph of y equals f of x at the point 1, 3 has a slope of 3 halves. So let's find f inverse of 3. So first of all, and I've used the book's notation in this example where it's f inverse with parentheses around it and then a prime to indicate that I'm looking for the derivative of the inverse function f. Okay, so we know the formula. We know that the formula is f inverse derivative of x is equal to 1 over f prime of f inverse of x. So let's take a look. Let's sort of decode. I'll put this aside and let's kind of decode the information that we're being given here. What we've been told is that the line tangent to the graph of y equals f of x at 1, 3 has a slope of 3 halves. Focus on this. This is one of the things that's important in this class, is to be able to get information out of a word problem. So what we have is, we know that the point 1, 3 has a tangent with that slope. So what that's saying is that f prime of 1, in other words, if I plug in this x value into the derivative, I should get the tangent line slope. Now, the other thing that we know, I'll put a 1 next to that. These are sort of things we know. The other thing we know is that if the point 1, 3 is, if this is a point of tangency to the graph of the original function, that means the point 1, 3 is on the graph of the original function. That means that the point 3, 1 is on the graph of y equals f inverse of x. So that's kind of a useful thing to know. And the other thing that we know is that f inverse of 3 is equal to 1. How do we know that? Because this point is on the graph. That means if I plug in 3 into the inverse function, I get 1. So now it looks like we really have all that we need to be able to answer this question. We can simply write that f inverse prime of 3 is equal to 1 over f prime of f inverse of 3. That's going to equal 1 over f prime of, we already looked here, that f inverse of 3 is 1, so f prime of 1 over f prime of 1, and looking up here, we determined from the problem, because we know the slope of the tangent line at 1, 3, we determined that f prime is equal to 3 halves. So that means that this is going to be 1 over 3 halves, which is 2/3. That's the slope. That's the slope of the line that is that's the slope of the line that's tangent to the inverse function at x equals 3. By the way, we could go on with this. I know that the setup doesn't ask for this, but we could answer the question, what is the equation of this tangent line? Let me write this out quickly. We can use the information to answer this question because what we know is that we know that the point 3, 1 is on the graph of the inverse function. So we have a point, and we also now know the slope of that. We know the slope of that tangent line. So just using point slope form, we can write out the answer and just write y minus 1 is equal to 2/3 x minus 3. That's a line that passes through the point 3, 1, which we know is on the graph of the inverse function and has a slope of 2/3. So that would be a follow-up question you can answer, and do that using the inverse function rule.